Algebra Lesson 3-7. At the beginning of the book, we were talking about variables, and we actually looked at a few different formulas. And then we left those formulas, and we started talking about equations. And now we're going to come back, and we're going to start looking at some more formulas. You notice the last time we were dealing with these problems, we had the distance equals rate times time come into play in numerous occasions in some of the problems that we were working on. So for our first definition, we want to go over formula, which is an algebraic equation that relates two or more real-life quantities. So they're still equations, just like what we've been working on. It's just that it's going to have to do with real-life stuff. For example, distance equals rate and time would be three different real-life quantities. It has to be two or more. And there are many different formulas, but I like to think formulas are very similar to recipes. As I've mentioned in the past, if you don't use the correct recipe for what you're trying to use or get, then it's not going to come out right for you. If you're dealing with distance, rate, and time, it would be silly to use the simple interest formula. But I heard the word rate in simple interest. You did. But it's a percentage rate versus a speed rate. So the right formula is crucial. Also, making sure that you put the correct values in for those variables is very important. As I mentioned in the past, if you're making cookies and you accidentally put the amount of sugar and you use salt instead, 2 cups of salt is going to make your cookies taste terrible. So the correct recipe, the correct formula for the correct problem is very important. But remember, a formula is really just an equation that has at least 2 different real-life quantities. All right? Now, a function. We talked about functions when we were making input-output tables. And we stated that for every input, there was exactly one output for that input if it's truly a function. We also said, it was a little tricky, that it's possible that a lot of different inputs could result in the same output. There's nothing wrong with that. We just can't have a number go into a function and create a 5, and the next time we put it in, create a 7. That wouldn't be a function. A 2-variable equation, maybe x and y, maybe a and b, written so that one of the variables is all alone on one side of the equal sign. Now the ones we worked on earlier when we were making our input-output tables look very similar to this. Y equals 2x plus 3. That was a function. It has 2 variables. It's written so that one of the variables is all by itself on one side, equal to the expression of the other variables. Right? So that's an example of a function. Now, I'm going to give you some more examples of functions that are also similar to formulas. I'll give you examples of functions and how they would not look if they were not functions. So here we have the temperature conversion formula going from Fahrenheit into Celsius. If you want to know what the Celsius temperature is, you would plug in the Fahrenheit temperature here. Say it was a 70-degree day. You'd take 70 degrees and subtract 32, and then you would end up having another number as a result of that. So 70 minus 32 is going to be 38. You'd take that 38 and you'd multiply it by 5/9. Now 5/9 is close to half. It's a little bit more than half. So a moment ago I had 38. Half of 38 is 19. This is going to be a little bit more than 19. Maybe we would approximate it somewhere in the 20, 21, 22 degrees Celsius range. Now you could multiply by 5 and divide by 9 and you'd get the exact value. This is the same formula, but I rewrote it so that it wasn't as a function. Notice that it's 0 all alone rather than a variable all by itself. The way I rewrote it is if you wanted to get rid of this c, you would subtract c from both sides. So there's the subtract c. Now it's equal to 0. It's the same formula, but it's not written as a function where one of the variables is all alone. And another example, p equals 4s. P stands for perimeter, and you would take the 4s, this is the perimeter of a square. So all sides are the same on a square, so perimeter equals 4 times whatever the sides are. That is in a function form because it has a variable all alone, and it still has 2 different values, 2 different variables in the problem. If I were to write it p over s equals 4, in other words, divide this side by s so that s came over here. If I divide by s, they'd cancel out and 4 would be alone. This is not as a function because one of the variables isn't alone. They're together. So you're still going to be practicing dealing with the same type of information, which are equations. You're just going to be playing the shuffling game with the letters, not always just numbers. You can rearrange formulas in many different ways. For example, say we have the simple interest formula, I equals P times R times t. Now right now this is as a function because it has one variable alone. But what if it's not the variable that I want alone? What if I have this problem? I know this is the formula, but I really would like rate to be alone. If I want rate to be alone, that means I need to get rid of the p and the t so that r can be all by itself. Well, all right. The opposite of multiplying by p and t is to divide by p and t. And whatever I do to one side, I must do to the other. Now, in between this p and that t is really multiplication. And in between this p and that t is really multiplication. But what's happened is the p's have canceled out and the t's have canceled out. And I've isolated the letter r, which is exactly what I want. And I could say I over pt will equal the rate. So I've rearranged the simple interest formula to isolate the variable that I'm looking for. All right, let's try that again, but this time, let's say we don't want to get r alone. This time we would like to get t alone. Well, if we want to get t alone, it's the same concept. T is being multiplied by p and r, so I would divide both sides by p times r. What you do to one side, you must do to the other. Got some drag delay there. Alright, the p and the r on this side cancel, the r and the r on this side cancel, leaving us with the t that we want. That's what t is going to equal. I over p times r is equal to t. And you could do this for p as well. It really wouldn't matter. If you recall, at the beginning of the year, I gave you distance equals rate times time. But I also gave you a number of other forms of this same formula. I gave you where t was alone. And in order to get t alone, you would divide both sides by r. And if you recall, I said t is equal to distance divided by rate. But maybe you wanted to get r alone. So d equals rt, and you want to get r alone, you would divide by t. And in the process, r is now alone. R now equals distance over time. So you recognize these two formulas as variations of the d equals rt model, and it's the exact same shuffling game. Whatever you do to one side, you must do to the other. If you want to remove something from one side, you use inverse operations to remove it and move it to the other side. None of these examples that I just did have any numbers in them. They were all letters. Yet removing a letter from one side of the equal sign to the other involved the exact same process that it did when we had numbers. Inverse operations. If you see a +2 and you want to get rid of it, subtract 2 or add -2, but make sure you do it to both sides.